Now we are going to see the second one, which is ring modulator. Our diodes are arranged in such a fashion of ring, therefore it is referred to as ring modulator. It is also mentioned it as switching modulator. In our conventional AM, we have seen switching modulator, which we have used for high level modulators. For low level modulators, we have used square law detectors, because square law detectors will operate in a non-linear region and switching modulator will operate in a linear region. This we have already seen. Switching modulator is preferred for high level modulation and switching modulator will operate in a linear region. Now we will see the circuit diagram for the ring modulator. Message signal M of t is applied to the transformer. We have used here a double tuned transformer. We can use a central tapped transformer here. Diodes are arranged in such a fashion that it looks like a ring. The output of we are going to take this transformer as T1 and this transformer as T2, and here the diode, this diode we are going to refer it as D1 and the second diode as D2, and the third and fourth diode are interconnected like in this way. This is our D, we refer it as D3 and we refer it as D2 and D4. Odd numbers in the upper path and lower path and even numbers in the interconnected path. Therefore, inside and outside, if we refer this circuit diagram as outside part and inside part, outside part will contain the odd numbers and the inside of the circuit diagram will contain the even numbers. Therefore, the diodes are arranged in a ring fashion. We refer this as point A and this as point B and this as point C and this as point D in order to study the working of the circuit diagram. And here we are going to pass the C of t, which we refer it as carrier signal. The input applied here, it is referred as V1 of t. This is our message signal, and here we, after passing through the diode configuration, we are referring it as V0 of t, and the modulated output is filtered by using the band pass filter. We use a single tuned or double tuned filter. Here we are going to get the modulated output of double sideband suppressed carrier. Here the message signal, we know that M of t is nothing but AM cos omega M of t, and for the carrier signal we are going to apply a periodic pulse train of a square wave. Positive amplitude as my +1 and my negative amplitude as -1. So this is our square wave carrier. Since we are having a periodic pulse train, we are going to analyze it by using the Fourier series analysis. Therefore, the Fourier series representation for this periodic pulse train is given by C of t is equal to 4 by pi summation over n is equal to 1 to infinity minus 1 of n minus 1 divided by 2n minus 1 cos of 2 pi fct 2n minus 1. So this we are going to take for the second signal. First signal is our M of t, which we refer it as AM cos omega M of t. Therefore, the modulated signal we will take here. Our modulated signal, if we take our modulated signal as this, when we modulate this modulate signal using ring modulator, the resultant output will be here. This is a time domain representation. So it acts like a switch. Therefore, for this particular period, it will be on, again off, on, off. This clipping will happen. And phase reversal at the zero crossing. So it will go on like this. This we refer it as DSB SC waveform. When we have a positive half cycle of the input, that is when we have the positive half cycle of the square wave signal, our message signal will be for the positive half cycle. Our D1 and D3 will be conducting and D2 and D4 will act as an open circuit. Therefore, we will have D1 and D3 in a conducting mode, D2 and D4 in an open connection. Therefore, only the current will flow in this direction since it is forward biased. Our input cycle, which is having a positive cycle here, this is our M of t and this is a t. So we have a rectangular pulse train here which is applied to the central transformer. So when we have a positive half cycle, our current is greater than 0. Therefore, then D1 and D3 will be conducting and D2 and D4 will be in open connections. Therefore, our transformers and transformer T1 and T2, we have here two transformers. One we refer it as T1, another we refer it as T2. These two transformers will be in phase together. That is, that phase difference between T2 and T1 is 0 degree. No phase shift. There will be no phase shift. Therefore, A and B are connected, C and D are connected. Now, if we have a negative half cycle, this is for ring modulator. So, when we have a negative half cycle of the input, what will happen? Here we are going to apply the negative input. Therefore, D1 and D2 will get reverse biased and D2 and D4 will get forward biased. D1 and D3 will get reverse biased. Initially, it was in forward bias stage. Now, it moves to reverse bias stage. Here also forward bias and then reverse bias. Here reverse bias and then forward biased. Here reverse bias condition and then forward bias condition. Therefore, now our D1 and D3 will go to open condition and D2 and D4, the diodes which we are lying in the inside of the circuit will start conducting. Therefore, A and D are connected, C and B are connected. A and D are connected and then C and B are connected. This will make transformer T1 and T2 will get a phase shift of 180 degree. That is, here we are going to get a M of t and now we are going to get the 180 degree phase shift. Therefore, we are going to get the minus of M of t. This is what we achieved in the previous balanced modulator configuration. This is the working part of ring modulator. Now we are going to see the time domain and frequency time domain representation. Then we will go the frequency domain representation of the ring modulator. We have just mentioned the Fourier series analysis for the periodic pulse train. Now, for the first two values, let C of t is equal to 4 by pi summation of n is equal to 1 to infinity and then minus 1 of n minus 1 divided by 2n minus 1. In this second equation, we are going to substitute n is equal to 1 and then n is equal to 2. We are going to take only the first two terms for our derivation. We will rewrite the expressions for our convenience. M of t is equal to am cos omega m of t and C of t is equal to 4 by pi summation over n is equal to infinity minus 1 whole power n minus 1 divided by 2n minus 1 cos of 2 pi fct 2n minus 1. Therefore, for the first two terms, it will be 4 by pi cos of 2 pi fct minus of 1 by 3 cos of 6 pi fct plus etc. Here, when we substitute 1, 2n minus 1, therefore it will be 1. Here the same term will be retained. Here this part will become 1. Therefore, cos 2 pi fct, when you substitute 2n minus 1, therefore 2 2s are 4, 4 minus 1 3, 3 2s are 6, 6 pi and here this minus part will become minus 1 by 3. Therefore, our output at V naught of t is given by m of t into c of t, the simple product multiplication. Therefore, v naught of t is equal to 4 by pi m of t cos of 2 pi fct minus 4 by 3 pi m of t cos of 6 pi fct. By taking the Fourier transform, this is our equation. Refer this as equation number 3. Refer this as equation number 1 and 2. Therefore, the product multiplication of m of t and c of t will give the time domain expression. We know that taking Fourier transform, we will be getting v naught of f, which is equal to 2 by pi m of f minus fc. The Fourier transform pairs for message signal with the cos of 2 pi fct, will get m of t, m of f minus fc plus m of fc divided by 2. Already we have 4 in the numerator, therefore we will get 2 by pi m of f minus fc plus m of f plus fc as final product. Here also 2 by 3 pi m of f minus fc plus 3 fc m of f plus 3 fc. So this is our equation number 4. This is our Fourier domain Fourier representation, Fourier transform for the message signal and the carrier signal. This signal is v naught of t. When it is passed through a band pass filter, only the particular range of frequency will be filtered through the band pass filter. The remaining unwanted terms, whether it may be low frequency term or a high frequency term, apart from the desired frequency, it will be eliminated. Therefore, here this is our desired frequency and this is our unwanted term. So this will be filtered out by using the band pass filter. The output of band pass filter will be given by S of t, which is equal to 4 by pi m of t cos of 2 pi fct. This is our required term. When you plot the spectrum, we can easily identify which are all the high frequency term and which are all the term required for the modulated signal. So for the first, we are going to plot m of f minus fc by m of f plus fc. So this is our m of f minus fc and this is our m of f plus fc. Therefore, m of f minus fc, m of f plus fc, this is fc term and this is minus fc. The whole bandwidth is 2 fm and the next the second term is plotted as for the center frequency 3 fc. This is the high frequency term for m of f minus 3 fc and m of f plus 3 fc. The desired cutoff frequency for the band pass filter will be within this region. Therefore, only these sidebands will be filtered through the band pass filter, and this is our equation number 5. This is our final double sideband suppressed carrier time domain expression. Therefore, our 3 fc minus of fm should be greater than, here the cutoff is fc plus fm. Therefore, should be greater than fc plus fm, or else these two signals will get overlap and it will make our band pass filtration difficult. Therefore, our fc should always be greater than fm. Carrier frequency should always be greater than the message frequency. Now we are going to see demodulation of double sideband suppressed carrier wave. We are going to see 3 topics under this. One is coherent, which we refer it as synchronous detection or demodulation, that is the reverse process applying in the generation side. Modulation is applied in the generator part and demodulation is to recover the modulated wave in the receiver part. Costas loop receiver which is using the negative feedback system. The third, we are going to see carrier reinsertion technique. Which is by using the envelope detector. We name it as for low level modulation, or we can also refer it as non-coherent or non-linear detector. Now the first topic in the demodulation is coherent detection. Coherent implies that the carrier frequency used in the transmitter side must be in phase and having same frequency as that of the carrier used in the transmitter side. Therefore, the oscillator used in the transmitter side and the receiver side both should have the same frequency and same phase in order to recover the message signal using the coherent or synchronous detection. We know our message signal is equal to m of t am cos omega mt, and our carrier signal c of t is equal to ac cos omega ct. It's a direct product multiplication. Therefore, s of t when multiplied, this is our local oscillator, product multiplier, s of t, this is our amplitude modulated wave. When it is multiplied with the local oscillator carrier signal, our output will be m dash of t after it is filtered by using the low pass filter. Here we are going to have a low pass filter to achieve the message signal, to filter out the message signal from the recovered signal. We know s of t is equal to m of t into c of t. Therefore, s of t is equal to m of t into ac cos 2 pi fct. This is the signal we are going to apply into the detector. We refer it as equation number 1. Here the initial output is referred as V naught of t. After passing through the low pass filter, it is referred as m dash of t. Therefore, the output of V naught of t is given by V naught of t. The output is the modulated signal is multiplied with the c of t, which is the carrier term. We refer it as cos of 2 pi fct. Fc, the transmitter and receiver side are incoherent with each other. Therefore, there will be no phase difference or frequency difference. S of t into cos of 2 pi fct, we refer it as equation number 2. The multiplication of this 2 will give, we have written the expression for V naught of t. V naught of t is equal to S of t cos 2 pi fct, and we know that S of t is m of t ac cos of 2 pi fct into cos of 2 pi fct. We know the trigonometric representation for cos square 2 theta, which is equal to 1 plus cos square theta is equal to 1 plus cos 2 theta divided by 2. Therefore, by using the simplification, m of t into ac cos square 2 pi fct will result into m of t ac by 2 plus ac m of t cos of 4 pi fct divided by 2. So, this is our V naught of t. When this signal is applied to the low pass filter, a high frequency term will get eliminated. Only the low frequency term will be passed to the low pass filter. Therefore, the output of low pass filter m dash of t will be m of t into AC by 2. This is our desired message signal. By taking the Fourier transform also, we can refer it as. Therefore, for our convenience, we are again taking the Fourier transform m of f into AC by 2 plus AC by 4 m of f minus fc. In order to emphasize the fact of which is our desired signal and which is our undesired signal, we are taking the Fourier transform for this equation. Mention it as equation number 3. Therefore, this is our equation number 4. This is obtained by taking the Fourier transform of equation number 3. If we plot the frequency domain representation for this equation, and this is going to be our message signal minus FM and 0, and this is our, again we are getting the modulated signal in the output waveform. So this is our my FC term and this is our minus of FC. The low pass filter, this is the second term and this is the second term. AC by 4, AC by 4, and this is our AC by 2. The low pass filter is going to have a cutoff frequency less than that of FC minus of FM. This cutoff frequency should be greater than the frequency of message signal. This is the cutoff frequency for low pass filter. So this is our desired signal. We have recovered the message signal from the coherent detection. If we have already seen in the conventional AM coherent detection part, if we have a phase error, we'll get when our phase is equal to 0 degree, we'll have quadrature null effect. This part we have already discussed. Quadrature null effect. If we have phi is equal to if we have 90 degree, then if we have 0 degree, 90 degree, then we'll have a quadrature null effect. If we have a 0 degree, there will be no phase error, which will refer to the coherent detection. 0 is equal to 180 degree, then it will give negative, that is inversal, phase inversal. So these are all the effects which we have already studied. If we have a frequency error in the local oscillator, then we'll have either the overlap or we may be ended with a situation of not extracting the signal, which we already discussed. Now we are going to see the second one, cost as receiver. It is using the, we have already mentioned it as, it is going to use the negative feedback system to suppress the carrier. We'll saw the circuit diagram first, then we'll refer the working. Here, this is our modulated signal which we are applying to the receiver part, and here we are having the product modulator. And here we are having another product modulator similar to that of the balanced configuration, but instead of using the same carrier on both sides, we are going to use a negative feedback system. So here we are having the VCO, voltage control oscillator, and here we are going to have the phase discriminator to nullify the phase difference. Here to get the VDC. The output of the product modulator is applied to the low pass filter, and here it is applied to the low pass filter as well. M dash of t, and here again M dash of t. This is the output of M dash of t, which we call it as AC by 2 into M of t cos theta. And here is the important part. This voltage control oscillator will give the output as cos of 2 pi fct plus theta, and here we are using the minus pi by 2 phase shifter and then applied to the product modulator. Therefore, our cos of 2 pi fct plus theta will become sin of 2 pi fct plus theta. Therefore, we are applying the modulated signal S of t to the product modulator. The one of the input for the product modulator is the carrier signal cos 2 pi fct plus theta, and the another input for the product modulator here is inverse of, that is 90 degree phase shift by using the phase shifter, 90 degree phase shift, and then the carrier signal is shifted 90 degree. Therefore, when it is cos, it will become sine of 2 pi fct plus theta. It will apply to the product modulator. The resultant is from the both product modulator applied to the low pass filter. Then if we have any frequency or phase deviation that will be passed through the phase discriminator, it will nullify the phase difference. Therefore, our output signal will get the message signal after suppressing the carrier. It consists of the upper channel, we are going to refer it as in phase coherent detector, and the lower channel we are going to refer it as quadrature coherent detector. In short, we refer it as I channel and then Q channel. I channel and Q channel are interconnected in such a way to achieve the negative feedback system. This negative feedback system has an objective to maintain the local oscillator carrier in phase with respect to the carrier oscillator used in the transmitter side. These two are helping to achieve the negative feedback system. So when our theta is equal to 0 here, when our theta is equal to 0, output of I channel will become AC by 2 into M of T. Q channel will become, output of Q channel will become 0, because sine 0 will be 0. When our output is second condition, when we have output not equal to 0 but will we have a small value of DC signal, then it will be eliminated by using the phase discriminator. Therefore, operating point of VC is always maintained at phi is equal to 0. Whenever it goes greater than or less than 0, this phase discriminator will come into role play, and then it will eliminate the small amount of DC variations, and then it will try to maintain the local oscillator carrier frequency with respect to that of the transmitter side. The third one is the, in demodulation we are going to see is the carrier reinsertion technique or envelope non-coherent detector. That is, we are going to apply the S of t and the oscillator AC cos of 2 pi fct plus phi. Then the resultant signal is V of t, which we are going to obtain the applied to the envelope detector. This we are referred as carrier reinsertion technique, because envelope detector, it is just going to follow the AM envelope. We are inserting the carrier and then we are going to suppress at the output of the envelope detector. This phase error, if I represents the phase error, it must be 0 for coherent detection. So this adding the carrier wave, then passing the resultant wave to the envelope detector will give the output of double sideband. Here it is the double sideband suppressed carrier amplitude modulated wave. So by again inserting the carrier, we are going to get the M dash of t, that is the recovered message signal. So we have seen balanced modulator in the demodulation side, and the co-stops receiver, which is applying the negative feedback system, and the carrier reinsertion technique, which is by using the envelope detector. We have seen the 3 demodulation techniques. We are going to see the one application using the slight modification of the co-stops receiver, that is by using the negative feedback system. How we can simultaneously pass 2 message signals: quadrature, carrier, multiplexing. This is one application of double sideband suppressed carrier, one of the application. It can be also referred as QAEM, quadrature amplitude modulation, because since it is employing double sideband suppressed carrier, which is coming into the amplitude modulation category, therefore it is also referred as quadrature amplitude modulation. It is contained either one sideband is sufficient to actually our double sideband suppressed carrier. This is suppressed, imagine it as a suppressed waveform. So for S of F, this is our upper sideband and lower sideband USB and then up LSB, and then here also USB, LSB and then USB. Either lower sideband or upper sideband is more than sufficient to convey our information. Therefore, we are using this property. Either LSB or USB is sufficient to convey our information. Therefore, we are using this property. By exploiting this property, we are going to use the quadrature carrier multiplexing circuit diagram to achieve how we are combining 2 or 3 modulating signal, and then how we are recovering 2 modulating signal at the receiver side. It shows how effectively we can transmit the 2 message signals in a combined way. Here we are having a product modulator and we are going to send the carrier signal. This is cos of 2 pi FCT, and we are going to use a minus pi by 2 phase shifter, and again as a product modulator we are going to apply M1 of t in the top and M1 of t to the bottom product modulator, and the resultant is summed together and then sent to the channel. Here is plus and here is also plus, and then S of t will give the multiplexed signal. These two are M1 of t and M2 of t are our message signals, and this is our carrier signal. This two represents our product modulator, and this is our 90-degree phase shifter. So by exploiting the property of using either one of the lower sideband, we are achieving the quadrature multiplexing, carrier multiplexing. Therefore, our S of t will consist of both the terms M1 of t cos of 2 pi FCT, it is having an amplitude of AC, plus ACM2 of t and sine of 2 pi FCT. Therefore, M2 of t, here we are going to have cos 2 pi FCT and here we are going to have AC sine 2 pi FCT. Therefore, M1 of t is multiplied with AC cos 2 pi FCT, M2 of t is multiplied with AC sine 2 pi FCT. Therefore, the resultant signal is M of t into AC sine 2 pi FCT here, and the resultant signal is AC M of t cos of 2 pi FCT here. This is our signal 1 and this is signal 2, and both are added together and we are getting the multiplexed signal as this. Now in the receiver side, we are going to again, this is our transmitter and this is our receiver part. Using the product modulator and again local oscillator cos of 2 pi FCT and minus pi by 2 phase shifter, this is our S of t modulated signal at the receiver side passing through the low pass filter to remove the unwanted high frequency terms. This is our V1 of t and this is our V2 of t. So here we are going to multiply our S of t with sine of 2 pi FCT, and here we are going to multiply our modulated signal with cos of 2 pi FCT and filtering out the high frequency terms. Here we are going to M1 dash of t and here M2 dash of t, 1 by 2 AC M1 of t, 1 by 2 AC M2 of t. For a reference, we'll just calculate for upper path and it will be similar to that of the lower path as well. Therefore, V1 of t is equal to S of t into cos 2 pi FCT. We know that since we have used a product modulator here. What is our S of t? S of t is AC m1 of t cos of 2 pi fct. From the equation number 1 we can write it as AC m2 of t sin of 2 pi fct, which is multiplied with cos of 2 pi fct. Therefore, AC m1 of t cos square 2 pi f of SC of t plus AC m2 of t sin 2 pi fct into cos 2 pi fct. Therefore, cos sin 2 pi fct into cos of 2 pi fct. This term we will written as 1 plus cos 2 theta divided by 2. By using the trigonometric formula, cos square theta is equal to 1 plus cos 2 theta divided by 2. Therefore, the final formula will be AC by 2 m1 of t plus AC m1 of t divided by 2 cos of 4 pi fct plus these two terms we can refer it as sin 4 pi fct, because then the higher frequency terms of sin A cos B form, the high frequency terms are eliminated. Therefore, our input signal, these two terms and these terms will get eliminated, and our signal will be AC by 2 into m1 of t. This is our recovered message signal. Similarly, for V2 of t, AC by 2 into m2 of t. Coherent detector must be available. That is, here there will be no phase difference or no frequency difference. We have not used any negative feedback system to nullify the phase difference or frequency difference. We have simply applied the phase shifter here. Therefore, by using the balanced configuration of the product modulator, we can simultaneously modulate two message signals, and here we can at the receiver side we can recover our message signal 1 and message signal 2. The phasor diagram. The phasor diagram will be, we know that since carrier is suppressed, we will have only the upper sideband and lower sideband. Therefore, upper sideband will rotate in the anti-clockwise direction, lower sideband will result in the clockwise direction. The resultant is our AM envelope. This is our voltage of DSB SC. This is our VUSB. This is our VLSB. This is our resultant vector addition of two signals. We are going to see disadvantage. Even though the power factor we have achieved 66.67%, but bandwidth is twice the FM. Therefore, we have not achieved the bandwidth reduction, we have achieved only the power distribution efficiency.